Welcome to another GC Basic demonstration. This is part 8 for the 18FQ24 chip family. This is showing serial data. So we're going to move on from where we were previously. We have connected up some LEDs. We're actually going to send some data from the microcontroller to the terminal attached to my PC, and you can do the same. And it's a great way to debug, show information, etc. Fantastic way. It is. I would strongly recommend everyone gets this sorted. So like and subscribe. If you like and subscribe, the metrics will go up. More people will find the channel, which is what I want. So number 8. After this, we will essentially be diverging away from what I would call the typical microchip low pin count demonstrations. We'll be looking at timers and overflow and getting into some really interesting areas. This has been interesting so far, and this is by far one of the better ones of the series. So let's go back. I'm assuming that you've installed your software. You've got a programmer that's operational. You have a Q24 attached, and you have the LEDs operating a pot, switches, and you've added in a USB TTL converter, which I shall talk about in a moment. In terms of hardware, I've changed the configuration to add in this serial connection. I'm going to connect it on port C.6, and I put the TX in our little map. And what's important about this is I've chosen that. I had to choose it, and I'll show you how I chose that. And you could put that on any of the valid ports. It's up to you where you put it, but I like it in that area there, so I've chosen port C.6. And so I put it in here. And what's important, and that's my TX, meaning transmit, is that I could have gone anywhere, and that's using something called peripheral, something select, PPS. We're going to use PPS to tell the microcontroller to connect this transmit or USART activity to that port. But there is something also very, very important, is that this diagram for this particular chip has what's called power domains. And that power domain is the following. You apply voltage to the VDD. I've supplied 3. You could supply 3V3. I don't care which one you do. You must also provide power to this domain, VDDIO2. And what is really important is if you do not apply it, the green pins, which are down here, look, the pin on VDDIO, that's its power domain. These pins, because they've got little green tags on them, look, would not have the right power level on them. So if you don't connect up what used to be connected to here, well, this used to be called C.7, if you do not connect voltage into here, either whatever voltage you want, it will not work. If you don't put anything in the VDDIO2, this chip will fail, and I'll show you that failing. We'll do that in a moment. So I said that we're going to have an output on the universal synchronous asynchronous receiver transmitter called USART. We're going to push it out through this TTL USB. Now we're going to use the tutorial we had so far, but we're just going to put the serial data out. And this is what one looks like. And you can get these on most of the marketplaces now, and they're extremely cheap. So you need to connect a common ground, must be a common ground. I connected up to the board itself. And you must connect up the RX because this thing is receiving. So you connect the TX of our chip, the TX to the RX here, and then it goes off to the PC. And it shows up as a communications port, and we'll see how we connect to that very shortly. And I've got one connected. I'll show you that. So let's stop there and we'll look at the desk cam. Oh, there we go. Bit of a tilt on the older camera there. I've got my chip is here. LED still flashing, rotating on the potler as it was before. And over here, I have two connections. I have a yellow connection, which goes to the C.6, and the power domain on this pin here. You must have the power domain. Everything else will work apart from the serial, and I'll show you that failing shortly. So the rest of this hasn't changed. I've got LEDs, switches, etc. So if I push this switch here, I don't think you can see it at high speed. The LED changes direction, and that's where we left it. And what we're going to do is put some of that information on the screen. Okay, so with that in mind, let's go back to this peripheral pin select. It does need configuring. It's the only method to set the functionality to the I/O pin. If you don't have PPS, it won't work. You can tailor where you put it. I put it on C.6, so therefore we must set the TX using PPX, and we're going to set it on as per my previous diagram. We are going to put it on C6. Okay, and you saw I have actually got it connected. So what I'm going to do, I'm going to show you how to get to it using PIC-info, and then we're going to look at PPSTool to do the configuration. Great. Let's walk through what we're going to do then. So what we're going to do, eventually, we will initialize the chip as we were before. We will set up the serial. That's the only change from the last video, and we will send some values. The rest of this is exactly what we've just seen actually on the video, which is it's doing a for next loop. No, it's doing a do loop, reading the ADC, and then if I push the switch, the LEDs change in direction. So all we're doing these two extra things: send some values to the serial, but we've done the setup beforehand. So let's have a look at some sample code. Great. So this is the program we're going to actually adapt, but how I'm going to adapt it is I'm going to start with a complete new empty program to show you we can do that. So I'm going to pull up something called first sample. I've actually cleaned it out. There is no code in it at all. You can adapt any program that you like. So I'm going to put in our chip, and the first thing I'm going to do is type in hash, if I can get in the editor, hash chip, and then I'm going to put this chip in, which is 18F26Q24. There it is, and I'm going to run it at 64 megahertz, so I'll just leave that as it is. Okay, option explicit. Done. The first thing I need to do, as per our diagram, was set up the serial. So the first thing I recommend you do is do the PPS. So how do you get the PPS up? All right, we've done this before. Function key F4, go into PIC-info. From PIC-info, select your microcontroller. And once you've selected the correct microcontroller, as I have here, let me just zoom in a bit. No, I don't think I should zoom in. Maybe I can zoom in. Maybe I can't. Oh, there we go. Make sure we got it selected here at the top. And if the PPSTool is functional, not grayed out, you can just click it and it will take you into the PPSTool. It's a very good way of checking that the PPSTool is actually active for this particular chip, if that makes sense. So it knows that this is a PPS chip. So it will now try to open up the PPS chip tool for you. If that doesn't work, you can always go into the menu and select function key F4, and PPSTool is listed there. I'll do that whilst it's loading. Look, PPSTool. It's a quick way of getting to it. But the way of going through PIC-info is it will always make sure that your chip that you have selected has got the right. It's a PPS chip. Now, what it's doing, it's caching a load of files. Okay, it's getting a big list of files, and I am currently doing a backup on my computer, hence it's running a tad slow. Now, this is PPSTool. Let me zoom in if I can. If I can, I will. There we go. A list of chips. 26 Q24 is listed. Fantastic. Now we have an output. Transmit is an output. Therefore, therefore we look in the PPS outputs capability window, and in there, and you cannot see it because of the zoom level. I'm going to have to come back over here. I'm going to have to come into here, look, click it, and at the bottom it says TX1. TX1, it means there's 2 channels. I want number 1. And I'm going to assign that, if I go back into my zoom for you, I'm going to assign that to C.6. Press the add key. And now it has added a load of code on the right hand side. Well, that's the code that we're going to need. So I can take a copy of that. It says I've put that in the clipboard into the editor, and I can now paste that in complete, unchanged. And it has set up the PPS. It's connected the USART to C.6. That's one operation. Second operation you need to do is tell it what baud rate to use. Quickest way of doing that is underscore U, and it will have a little thing there called second option USR setup. And it needs these 3 constants. It needs to know the baud rate from using the constant USART baud rate, USART transmit blocking, I'll explain that in a moment, and the delay. The T8, so the baud rate I'll use is 9.6, hit tab, and it's now complete. So what does this blocking do? The TX blocking ensures it does not load the next byte into the buffer before the previous one has left. It checks the interrupts for you automatically. So the default should always be TX blocking because you don't want to push the data out so it corrupts the buffer. The second one is you can slow the inter byte transfer rate down, and you'd put it in there as a number of milliseconds. And that you might have to do that for slower computers, not microcontrollers. And with that, that is the setup done. What have we done? PPS, using PPSTool, and then we've used a macro, this underscore, look, we went underscore U, and it's got the actual text there. You don't have to remember it all. Okay, let's do a really simple program. Do loop. If I could only type things today, a bit tired. Do loop. H serial print. Let's look at some more syntax for some stuff, shall we? Okay. Let's look at this. Is the serial command. Look, H serial print. Hello world. And the IDE automatically put the quotes in for you. Hardware serial. Maybe I should have a couple. Ser print. Hardware serial print. That's what that stands for. So guess what? If I type in HSER, I get lots of other commands, and I want to do a carriage return line feed. So hardware serial print carriage return line feed. There we go. Wait for 100 milliseconds. That you've seen in the past. So that's the full program. We've done the configuration, set the baud rate, done some strings. Let's just program that. Now, it's clearly sending data out because we told it to. So how do you get that on your computer? Well, if you press function key F9 or take the menu option, I don't care which option you go down. Let me pull it down for you so you can see it all happen. Function key F4, terminal, TE, terminal, second option down there, serial terminal, function key F9. So I could have just pressed function key F9, but I wanted to show you the long way. It's opened up a terminal, and here it is. It's a very simple thing. And up the top left-hand side, it's got connect and rescan. These are the 2 things. I've only got one serial port connected. That's the one that I have connected to it. It looks like the one that was in PowerPoint. I can connect to that, and it's saying hello world. Well, let me reassure you that that's doing something because my LEDs aren't flashing. But this yellow wire is now carrying a serial connector into, it has a serial connection in here. And let's go to Zen mode. You can see it's flashing away hello world. And if I pull out my serial connector, it stops dead. because I pulled it out. I'll put it back in. Now I'm going to have to just reconnect. Here we go. Look, I'll just do it slowly for you. Disconnect from because I've disconnected it physically from my computer. Rescan. I'll just clear that down. Connect. It's now saying hello world. So it's done the reconnection piece for you. So it's constantly sending out hello world. Let's look at our demonstration program then, because that's quite clever. So reversible LEDs. Let's look at what we've got in here. We have got, have you got PPS set up? Oh no, that's an older program. That's the one that was in there before. Control B. This is called reversible LEDs with variable delay to serial terminal. Click on it. Control B to shut that down. Here is the PPS. It's the same PPS we just looked at, being pulled in. Here is the same three constants. We saw those previously. Now you can, I'll come back to that later on. So what have I changed down here? I've said some strings. HCR print, H serial print, coach turn line feed, put a string out there called GC Basic 2024, show the chip, a constant called chip name string at what frequency we're operating at, and then wait 2 seconds. So it's going to push a message out to the terminal. What else have we got in here? Well, it says in here, look, along with the code that was there before, it says HCR print less than left. So when it's going in the left direction, it's going to put this string on the screen. When it's on the right, it's going to put another string up. Hey, that's clever. So depending which way it's going to do, it's going to be rotating left or right. We'll put a string up. Then it says HCR9, which is the tab, put the value of the port that we've been showing, incrementing through, rotating, change that from a byte to a bin. So a bin is a binary number, or binary string, sorry, a binary string on the screen. And then finally, another tab, put out the value of the delay with a casual turn line feed. Let me just program that. Go into Zen mode. We'll bring up the terminal. Here's the terminal. We'll see that flash up. And we'll see the message flash up with our chip name. Oh, there it goes, look. Oh, wait, I should, oh, that's a bit nasty. Never mind. You can correct that on your own. No, I can't leave it like that. That code wasn't very nice, was it? Let's be honest. There wasn't it said here, it was all in one big string, look. I think there should be, personally, I think there should be a carriage return line feed in here in my program. I've just put a carriage return line feed in. All the blue stuff is all preordained, not preordained, but it's all in the compiler, so you can go and get that on your own. And I'm just pulling that terminal a bit closer so we can see it. GC Basic, that's the old one. There's the new one, look, at 64 megahertz, our chip, and it says it's moving to the left. And if you look at the binary numbers, they are actually rotating in sequence with the LEDs. And it says 210 because that is the rotational value, the current value of the potentiometer. So if I rotate the potentiometer full up, it says that's 50. And if I rotate the pot, it says 1000. Now, so what's it doing there? Let's look at our source code. Remember back we said scale our result between 50 and 1000. It's doing exactly what we expected. So what we're getting is a representation of what's happening on the PCB through the serial USART connection. It says it is waiting for 642 milliseconds. The LED is rotating leftwise. It's going 1, 1, 1, 1 every 642 seconds. And when I push the button, as before, it will go to the right. The value of the ADC does not change, therefore 642 milliseconds, and now it's rotating it to the right. So you have a full representation of what's happening through the USART. USART is a crucial component for debugging. It's a crucial component for communication. And we will use other protocols, but this one, I learned this seriously back when I was extremely young. It was the first thing I learned, and I still have my first set of tools that I used for USART debugging back in the day. And it's a great thing. And it will run to fantastic speeds, seriously fast. I'm using 9,600 baud. I think I tested this chip the other day to 350,000 bits per second. It is fantastically quick, okay? You don't need to stress this thing out. Now, if you change the frequency of the chip, nothing changes in terms of the USR because the compiler recalculates all the settings. Let's just do that in our compiler. We're going to pretend for one moment that we need to run, because of power, our compiler at 1 megahertz. Function key F5 to compile our new option, and we will see it will say on our string that it's the same chip, but it will say it's running it at 1 megahertz, and we'll see that because I'm going to disconnect it after it's compiled it. Has it compiled it? Yeah, it's because I'm doing a backup over here. Look, my backup's carrying on. I think I've stressed my computer out. So if we look at what just came on the I've stopped the terminal. I've said it's 18F26Q24 at 1 megahertz. Notice that the strings and all the data is still being displayed because the compiler has recalculated the bits per second settings inside of the source code for you, fully automatic. So what I wanted to show was sample code, done that. I wanted to show you the power domain stuff. Now, I will restart this, and you can see that that is rotating quite nicely, and that's happening quite fast, quite nicely. I'm putting it down to 100 milliseconds-ish, because it's all ish, isn't it? There we go. Power domain is connected. Watch. I will disconnect the power domain. You get gibberish on the terminal because the voltage is not consistent. Let me reconnect that. On my board, I'm quite fortunate. I've got this capability. And the moment I reconnect the power domain, the voltage inside of that internal circuit becomes correct, and it all works. My power domain is currently set to 5 volts. I can change the power domain to 3.3. Notice as I lift it up, you get corruption. As I put it back down, 3.3. So I'm now running the microcontroller at the main voltage of 5 volts, and this particular power domain of serial at 3.3. So if you had a sensitive circuit, this is the way to control sensitive circuits. You can run them at 2 different voltages. I will take that back. And there we go. You can see power domains in operation, and they're very important that you keep the voltage correct. So I wanted to show you quick power domain. So with that, we're going to forget what we've been doing so far and move on to timers, timer overflows, 8-bit timers, 16-bit timers to flash these LEDs. Up to now, we've been using calculated delays. We'll be using the timer capability of the microcontroller and then move on from there. And with that, enjoy.